welcome to the numerical ship and offshore hydrodynamics. So, today we are going to discuss how numerically we can find out this b tau and the A infinity. Okay. So, that is what it is. So, if you remember in the last class we derived the equation of motion using impulse response function, also the relationship between the b tau and b omega. So, today we are going to see that how numerically we can get the value for b tau if I know the frequency domain solution which is b omega. Okay. And this is something that you have to use to get the this lecture. Okay. So, let us jump into the solution. Now, here actually that is how we finished in last class. So, now today we need to find out numerically how actually we can get this solution for b tau. Okay. Now, here if you this integration it is ranging 0 to infinity. However, you know that that if I plot this graph of b omega, now it is if I plot b omega versus omega, mostly the graph should look like it is very low frequency, it is 0 and then you have high frequency, and then I mean ideally it should be like this. The point is at some point this b goes to 0, right. So, let us take at some omega n, I can really find that okay, let me write in little bit bigger to understand it. So, at some omega n this graph should go to 0. Okay. So, having said that I have this understanding on this. So, this limit infinity when you calculate numerically it is not really till infinity, right. But here remember that the tau also here is a vary over the tau. So, here I have to get b 0 when tau equal to 0, and if you increase this tau with some increment delta tau, right. So, then I need to get b 0 and then b of delta tau, then b of 2 of delta tau and so on, right. Now, looking at this this expression, then what comes in our mind then, because I know this b omega is this graph. So, therefore, if I divide this with number of sections and simply if I use the trapezoidal rule that will do for me, and in fact, which is very true if you calculate for the b 0. Now, why? Because now let me write again this b tau is equal to 2 by pi into 0 to infinity into b omega into cos of omega tau into d omega. Now, here if I now it is true for beta 0. Why? Because if you take b 0, it is nothing but 2 by pi 0 to infinity into b omega into d omega, because cos of omega tau equal to 1 at tau equal to 0. So, we know that. Now, here it is nothing but the area under the curve, right, because again if I draw this curve once again, this side if I call this small b omega and this side if I call the omega, and I know this is going to like this in some omega n. So, definitely it is a finite graph, and this graph if I split in some regular interval, right, which we can call as d omega of course. in this regular interval, if I cut this, so eventually actually I can get a number, a real number definitely, because this is a finite. So, I need to modify, or I can modify this equation. Let me give a number to this equation. Let us take okay, I have 1, 2, 3 with continuation of that thing, we can keep it as a equation number 4. Okay. So, this equation number 4 and then it will just take equation number 5. So, then now from this 5 actually I can say that this B 0 equal to 2 by pi, and it is really not infinity, right. So, it should be some 0 to some omega n, which is finite value, then I need to calculate this B omega into d omega. So, this is a standard trapezoidal will do this one, right. Now, what happened for B delta tau? Let us see. Now, if I try to do the same with B delta tau, then what I get is 2 by pi 0 to infinity B omega cos of omega into delta tau into d omega. Now, you can say that okay, what is the big deal over here, because in last thing I just integrate using trapezoidal, now instead of b omega, now I can integrate b omega cos omega into delta tau. Okay. Delta is I just call nabla. Okay, no problem. Now there is a problem. So, what is the problem? This is problem because of this inclusion of cos omega into delta tau. Why? Because if you see over here, the only thing is changing over time is nothing but the cos omega into delta tau. Now, people not you do not realize this if I plot the graph of cos t or cos omega t, it is a sinusoidal like this. So, now the tau here, this tau is nothing but some multiple of delta tau this side. So, now there is no problem with my b omega, right. Now, what is happening, this cos term, since it is having m into delta tau, so nature of this cos actually influence the solution. So, therefore, if I now try to calculate from this equation using the trapezoidal, so then here it is b delta tau equal to 2 by pi into 0 to, now it is some omega n of course now, right, and then we have b omega into cos of omega into m. Okay, now in case of a m equal to 1, so m delta tau into d tau. So, this is the equation. Now, if I try to do b into m into delta tau, which is happening 2 by pi 0 to omega n b omega into cos of omega into m into delta tau into d tau. Now, here clearly this depending on this omega into m into delta tau, this functional value. So, therefore, I can understand this is again turns out to be some kind of repetitive function. It should, I mean it would be, because it is I just put the functional value. So, what we expect is then this function, this b tau function again should repeat the same thing, something like this, again something like this. I mean I am guessing, because of this equation it should repeat, right. Now, before we do anything here, let us try to understand the nature of the solution also. So, let us try to understand what would be the nature of the solution for b tau. Okay. Now, I know that this is nothing but 2 by pi. Now, even if you take it is not infinity, some kind of omega n, okay, into let us say b omega into cos of omega tau into d omega. So, let us try to understand what would be the nature of this solution. Okay. Now, the simple thing is that let us assume that b omega is something, some constant c. This is a simple way of understanding what would be the nature of the solution b tau. Okay. Now, let us assume it is nothing but b omega is a constant. So, what I am assuming? I am assuming that over this b omega and omega, it is something a constant throughout. Okay. I know this is a very very vague assumptions, but this really helps, very simple thing helps you to understand that that what would be the nature of the solution, something like this. Now, you see, now using this we have beta equal to 2 by pi 0 to omega n, and then it is cos of omega tau into d omega. Now, if you integrate this term, then definitely you can find out, if you integrate this thing, definitely we have 2 by pi, and again we have 1 upon omega multiply this functional value, right, as 0 to omega n. This is elementary, I really I do not care about this. Okay. I mean it is of course, it is a sine function, but I really I do not care what is here, because I know is this the modulus of this function, this equals to 1. So, it is harmonically it oscillates between minus 1 to plus 1. Most importantly, I in the denominator I have this 1 upon omega. Sorry, I integrating, sorry, I am very sorry, I am integrating with omega. So, I am sorry, it is omega tau, very sorry, because this integration is with respect to omega. So, I have 1 upon tau. Now, most importantly what we have this, we have in the denominator I have 1 upon tau. Okay. Now, you see I have b tau is equal to 2 by pi into tau. So, I have denominator a tau with some function and this function oscillate within a 0 minus 1 to plus 1, but because the sine function, right. Now, here when tau goes to infinity, because you see like that is what I want to achieve, right. I am trying to find out my b tau, and then tau starts from 0, then delta tau, 2 delta tau, 3 delta tau, in that way it is going m delta tau. Now, m can be anything, it could be infinity also, I mean very large number also. Now, in very large number I have the denominator is having a tau. So, now you see that this b tau should go to 0 when tau tending to infinity, because the numerator, the value of numerator always lying between minus 1 to plus 1. So, numerator does not go to infinity, but the denominator is going to infinity when tau tending to infinity, right. Before understanding or doing the whole thing, we need to understand this very basic thing. So, that actually that helps you to do this numerical thing, approximating the things, right. So, here now here you see that at tau equal to 0 I do not have this cos term. So, then it is integration from 0 to omega. So, now if we integrate this function, it is a some finite number, right. We can call some finite value k, right. And when tau goes to infinity and then b tau comes down to 0. So, we have to understand and we need to keep these things in our mind, that therefore, this nature of b tau versus tau should be with some constant value, because at tau equal to 0 I am doing the integration in the area under the curve, right. So, it must have some values and then it definitely somehow it should go to 0. It may not be the nature of the curve, it could be anything, but at least for larger tau it should go to 0, that is our take. Now, coming back to this, what we are discussing here. Now, if we do this, then this and we just put the functional value using trapezoidal rule, we really do not get this trend, right. So, then how we can solve it, right. So, mostly we can solve this by some kind of semi analytical method. Normally we prefer to solve this equation. Okay. So, here what we do as follows. Now, I have this b tau, let me write again this equation. This equals to 2 by pi, it is 0 to infinity, then b omega into cos of omega tau into d omega. So, this is the basic equation that actually we started. From there we come up with the idea is, since the graph of b omega is a damping curve which is at very low frequency and very high frequency, it is approaches to 0. So, definitely it should be 0 to with some infinity, right. Sorry, not infinity, with some value omega n, right, and then it is b omega into cos of omega tau into d omega. So, this is my step 1, realizing that the graph of b omega cannot be infinitely long, it should truncate, I should truncate at some point where that value of b omega is very close to 0. So, at that n I must truncate this value and then can split this integration over this, right. So, this is my second step. So, writing down the second step, it is b tau is equal to 2 by pi into 0 to some omega n into b omega into cos of omega tau into d omega. Then what we do? Then separately we calculate at tau equal to 0. So, I calculate b 0, which is 2 by pi 0 to omega n into b omega into d omega. So, this we called, and we can get this b of 0, right. Then I need to calculate b at some tau, b tau, right. Now, here we need to understand, we understand already, we have understand one thing, like we have understood one thing, like this tau definitely goes to 0 at some value of tau, but what is that value that we really no, we have that value actually we only get through experience. Now, normally we have seen that if you take for 80 second, then after 80 second it really goes to 0. So, trust me, it is sufficient to calculate this b tau for 80 second. Okay. Now then second thing that, so therefore, I understand that tau should be with 80 second. Now then the second question comes, what should be my delta tau, because this is something we really need to do, right, because it is b 0. So, the next step it should be b of delta tau, then b of 2 into delta tau and so on, right. So, then from here we need to find out what is the value of the tau should be 80 seconds. So, definitely depending on your delta tau. So, this solution also very easy, you can call some small into delta tau, that should be 80 seconds. So, from there I can get some idea about that, m equal to some integral value of okay, let me write this 80 by delta t plus 1, right. So, I understand that my m is the integer. So, it should be some integral value. So, I divide 80 by delta t, it could be real, it could be integer, I mean sometimes it is divisible by 80, it is integer, otherwise is a fraction. So, then just to make that I can take the minimum that value, I just simply choose my m in that way. So, the second thing also we have completed. So, the first thing we have to find out what is my n. So, that your omega n goes to I mean b of omega n goes to 0, this is my first job, and second job I need to calculate this m such that your that capital B into m into delta tau, that goes to 0 with that m. So, these two things, it is based on our experience we can set. Okay. So, two things is over. So, therefore, now again let us try to attack the problem. Again we have b into, now I can write m into delta tau, that should be is equal to 2 by pi and 0 to omega n. Now, this omega n also we need to write somewhere, let me do that. It is b omega into cos of omega into m into delta tau into d omega, right. Similarly, now let us try to look into the graph of b omega, and it is of course this omega n depending on how you are numerically define the b omega. Okay. Now, assume that this is your graph for b omega and this is your value at omega n here. Now, you are discretizing, it is now it is of course, it is b 0 and then you are discretizing with equal interval. Now, if you discretizing with the equal interval, and then we can define your d omega is equal to omega n minus omega n minus 1, that you can define. So, therefore, here you can write your omega n definitely some capital N multiplied by the d omega, right, fine. So, we also understand that, because you see this integration, ultimately this integration sign I need to replace by some kind of a summation sign, right. So, therefore, I have to you know we have to represent this omega in form of this n into d omega, right. Okay. So, now I know that my d tau or I know my tau equal to some small n into delta tau, and I also know my omega or you can say that tau m where the tau goes to 0 and omega n this equal to some capital N multiplied by the d omega. So, these two things I know. Now, my next job how I can define my b omega between two interval. Now, here the catch. Now, we can do that with respect to you can fit a curve, we need to fit a curve definitely, right, because these are the value I know, right. So, then how the b omega varies between these two lines, that we need to understand how b omega varies between these two lines, right, that we need to understand, right. Now, let us go with the most simple way. We assume that it will go here very linearly, right. So, therefore, in between let us take some interval is omega n into omega n plus 1 anything. So, this is the interval you can take or maybe you can take some omega n minus 1 or omega n, not I mean it is the way you feel comfortable you can take this, and then you can assume within this interval that your this variation of b omega is a straight line, right. So, therefore, we can assume this b omega it is a straight line. So, how we can write a straight line? So, b omega minus you can take this value, it is b, let us say omega n minus 1 should be equal to b of omega n minus b of omega n minus 1, and that is how we define a straight line, right. It is omega n minus omega n minus 1 multiplied by omega minus omega n minus 1. That is how we can define my straight line, right. So, now I understand, now actually now I am ready to attack this equation. So, what we do here, first I split it and I define this value of d omega which is omega n minus 1, and we define my omega n into multiple of n multiplied by the d omega. Again I understand that the tau, the maximum value of tau, it should be m into delta tau, right. So, with understanding we understand here that tau it is we need to till get the for 80 second, normally we are taking, let us take 80 second, and if it does not work then you can take 100 second. It is up to you, it is up to the experience how much tau you should take, but this should be equal to some m into delta tau, and this from here actually I can get the value for m. Okay. So, then the last thing what we did today is how I can define the b omega between the interval omega n and omega n minus 1. I assume a straight line approximation, right. So, therefore, this is something that actually we have to do before we solve this integration in using helping the semi analytic method. Okay. So, now I am ready to do the integration. So, in the next class we are going to see how with as I said is a semi analytic approach we find out the value for b tau for each delta tau. Okay. So, today we can stop here and in the next class we are really try to find out how we can approximate the b tau using the semi analytic methods, right. Okay, thank you.